It's that time of the year, Pi Day. Besides the number having a funny name, why do mathematicians celebrate Pi Day? I can go on why pi is really important. But in this video, I will try to show you possibly the most important and interesting example of why pi is celebrated. To truly understand the significance of pi, we will have to talk about two other important numbers, I and E. Let's start with pi, since that's kind of the focus of this video. Pi comes from the circle, specifically the ratio of a circle's circumference to its diameter, meaning if we took a piece of string and measured both the circumference and diameter, we will get pi by taking the circumference and dividing it by its diameter. And this applies to all circles, regardless of size. The reason why this discovery was important is suppose we had a ruler and no string. How can we measure the circle's circumference? If we do a little algebra, we can find the circle's circumference by multiplying the diameter by pi. This was a pretty significant discovery for the time. Archimedes is usually given the credit of discovering pi around 250 BC, and is even debated whether pi is actually referenced in the Bible. But this still doesn't answer why pi is so important. We have found the ratio of many other shapes. What makes pi different? Well, what makes pi unique is the fact that it's transcendental, meaning it cannot be expressed algebraically. Pi is also irrational, but so are all the other ratios. Irrational numbers cannot be written as fractions, or ratios, which is where the name comes from. Pi is special because it cannot be written algebraically, which is why mathematicians had to get really creative on how to define transcendental numbers like pi. Now let's talk about E, which is also transcendental. Unlike pi, it took us a lot more time to discover E. Jacob Bernoulli is often given credit for discovering E in 1683. He was really into compound interest and found E through a very interesting thought experiment. Suppose you put $1 in the bank with 100% interest compounded each year. That means you will get $2 at the end of the year. If the interest was 100% and was compounded twice per year, you will get 50% in the first half and another 50% in the second half, giving you $2.25 at the end of the year. Notice by increasing the number of compounding periods per year, the amount you get back increases. But what would happen if the compound frequency was infinite? Well, you will get E dollars back at the end of the year. If we plot this problem on a graph, by increasing the number of compounding periods per year toward infinity, you will get closer and closer to E. But Bernoulli did not give this number a name at the time, most likely due to our little understanding of the number at the time. The letter E came from Leonhard Euler, who is commonly seen as the greatest mathematician who ever lived. And finally, let's talk about I. I is commonly used for imaginary numbers. The definition of an imaginary number is the square root of -1. This is because if we think of algebra, everything has opposites. The opposite of addition is subtraction. The opposite of multiplication is division. And the opposite of a power is a root. Suppose we had the equation x squared equals 4. To find x, we can take the square root of both sides to get x equals the square root of 4, which gives us plus or minus 2. The reason why we have plus or minus is because if we square a positive or negative number, the answer will always be a positive number. This is why it's impossible to take the square root of a negative number, which is where the name imaginary comes from. Like negative numbers at one point, imaginary numbers were not respected like they are today. Because imaginary numbers are different from real numbers, we put them on a separate axis, perpendicular to the real numbers like this. This is commonly known as the complex plane. Now that we have covered all three, it's time to see the magic. You ready? E to the power of pi I is -1. Crazy, right? But why? Why is it -1? Well, this equation only tells a little bit of the story. This is the full equation. If we plug pi into the equation, we will get -1. The reason why this is so incredible is because if we were to plot this equation on the complex plane, we will get the unit circle. How interesting. And it gets crazier. This equation right here is the Fourier transform, which basically allows us to analyze any function by converting it into the frequency domain. With this information, we can draw anything we want by rotating a bunch of circles together, which is key for so many fields of science like electronic filters, audio and signal analysis, and even solving really hard problems like this, known as differential equations. Is all of this a coincidence, or was it designed by some higher power? It's examples like this that really makes us ask the question, does math prove a God exists? I mean, did you know that you cannot pen a mathematical equation because math is seen as a discovery rather than an invention, and that religion tells us that God is all-knowing and he only speaks the truth? Well, that literally sounds like math, the language of the universe. As always, thanks for watching, and I hope you liked this video and grew a new appreciation for the magic of mathematics. Peace.